All right. Let me share the screen. Okay, so let's start with some questions. Do we have any questions? Are there any questions?
No, sir.
All right. So last time we talked about, we discussed the Bohr atom, right? So today we are going to talk about the quantum nature of light. So this is a very exciting topic. So light, what is light, right? This is something that humans have been wondering for until since beginning of time. Without light, we don't have. Can you see my writing on the board?
Yes, sir.
Okay. So I don't know if you know, but Sir Isaac Newton believed that light was particles. I think he called them corpuscles, something like that. Okay, which in modern parlance are particles. Did you guys know that?
Yes, sir.
Yes, I've heard of it.
Yes, sir.
Okay. So, during Newton's time, there were others, most notably, I think, Christian Huygens. Who believed that light was made out of waves. Okay. Okay, and you guys perhaps know about Huygens principle, which is a way to describe the propagation of light by creating wave fronts from light fronts. Do you know about that? So Huygens, postulated the way that the light propagates. Suppose this is a wave front. Every point on this wave front acts as a source. And suppose that the wave is going in that direction. So every point on this wave front acts as a source, and it gives out spherical waves. But the intensity of the spherical waves diminishes as you go in the backward direction. And a moment later, the new position of the wavefront is then given by the envelope of these small wavefronts. Okay, so in that way, Huygens was able to describe diffraction, where light bends around barriers. So anyway, this was a debate for a long time, and the debate raged on, and it was not resolved in Newton's time or any time nearly afterwards. So it was at last in the 19th century, the debate was, seemingly resolved in favor of the wave theory, okay? Or the wave, yeah. And this was done largely through the work of a British physicist called Thomas Young. And Thomas Young, he was a master experimentalist, and he did the double slit experiment as a public experiment. Thomas Young did the double slit experiment. Where they saw the, just one second. Sorry about that. So Thomas Young did the double slit experiment, which exhibited the phenomena of interference. And this cannot be explained by a picture of light as classical particles, okay? And this established firmly the wave picture of light. Okay. Just one second. Okay, so are there any questions about this? The fact that, do you guys know about the double slit experiment?
Yes, sir.
Yes, we studied in the waves course.
Okay, anyone who hasn't seen it, and I can very briefly describe it then. Okay, so, it's a very, very beautiful experiment. Now, Thomas Young did that in the early part of the 19th century. In the later part of the 19th century, James Clerk Maxwell, combined electricity and magnetism, right? I should not say combined, I should say unified. Electricity and magnetism. So all of you know Maxwell's equations, but let me just write them down anyway, because you probably don't know the differential. Some of you may not know the differential form of Maxwell's equation. Anyway, yeah, let me just write it down just to motivate why motivate the next thing I'm going to say. So Maxwell's equations are differential equations in three-dimensional language. There are four equations. There's a divergence of E, which is plus is there a, yeah, I think that's it, right? Is a time-dependent part here?
Rho by epsilon naught.
Yeah. No, I know. Epsilon naught, I'm choosing units in which epsilon naught equals to 1 equals to mu naught equals to 1 equals to pi equals to 2 pi. Everything is 1, okay? So this is a very famous system of units. So
Wait, pi equals to 2 pi? Is that possible?
it's a joke.
Or won't these give wrong calculations results?
So this is basically, say, order of magnitude units, okay? But this is possible, okay? This is possible, where, and then divergence of B is 0. And then the time derivative of E is given by the curl of B. And I think there's so this is Ampere's law. And there is the time derivative of the magnetic field is curl of E, and that's Faraday-Lenz law, okay? And this is saying that there's no magnetic monopole. So, the precise form of these equations are unimportant, but what Maxwell was able to derive, and you can derive if you want, he was able to derive a wave equation from these equations. And the wave equation had, mu naught, epsilon naught going into it, and they combined in a way to give the speed of the wave to be c, the speed of light, okay? So in this way, Maxwell proved that light was nothing but electromagnetic waves. I should really put this in quotes because this is a very important nothing. Okay? So the picture that light is a wave seemed very, very well established by the end of 19th century. But of course, the crack in that picture appeared through the fact that the black body radiation was something that could not be explained via the classical statistical mechanics, where you apply classical electromagnetism, right? Now, but after the photoelectric effect in 1905, Einstein proposed that light energy was absorbed in quanta, that you could not absorb light energy in fraction. So, the photoelectric effect challenges the wave picture of light, right? And why is that? Because remember, what the photoelectric effect is that we have some metal, kind of some slab of metal, and we are shining ultraviolet light on it. And as a result, the metal emits electrons. Now, the electrons have a certain maximum kinetic energy. And if you increase the intensity of light, the maximum kinetic energy doesn't really change. All it does is that if you increase the intensity of light, more and more electrons are emitted. Okay? So if light was a wave, then of course, increasing the intensity would mean that electrons should be able to absorb more energy. But instead, that energy seems to be spread across different electrons. And on the other hand, the maximum energy, it grew linearly with the frequency of the light, and there was a
Work function.
work function, but I think it was negative. So if I think of the work function as something positive, it'll be okay. So, and Einstein was able to solve it by proposing that that a light, that kind of a photon carries a packet of energy of h nu. Okay, so this is very like strongly suggestive that light is a localized packet of energy contained in some sort of particle. Okay. So this is basically the motivation for what's going to come next. Okay. Any questions?
Are all type of energy quantized or just light?
That's a very good question. No, not all type of energy is quantized. So if you take a free, say, massive particle, say an electron. So I'm drawing it as a sphere, but it's actually a point-like object. So let's not do that. So suppose this is an electron, and it's not bound to any system. Its kinetic energy is not quantized. If the electron is free. However, if the electron is part of an atom, so if the electron is part of some atom, this is the cartoon picture of an atom, the Bohr atom, so to speak. But then the energies of the combined system is quantized. I should grammatically, to be correct, I should say energy. Okay, so, and we'll see that why. When we actually develop wave mechanics, we'll see why bound systems naturally have quantized energy and unbound systems don't have quantized energy. Okay, any more questions? That's a very good question.
Yes, sir.
Yeah.
In that last tutorial, we worked with the free particle, free harmonic oscillator, and we imposed some condition and proved that energy is quantized. The factor of Planck's.
Harmonic oscillator is not free, right?
Sorry?
The harmonic oscillator is a bound system. It's not a free system.
Oh, okay.
Right? Because the potential of the harmonic oscillator,
like in one dimension, like just left
yeah, it's
and
in
right.
one dimension. That's a dimensional thing. You can generalize to higher dimensions, but the potential energy of the harmonic oscillator is half kx squared, right? So if I plot this, we have something like this, right? So with the total energy Kaushik, I think we're getting a lot of interference from your end. Can you mute your microphone?
Hello.
Can you mute your microphone? We're getting a lot of interference from your end.
Okay. Okay.
Okay.
It's the
So,
fan.
yeah, sorry about that. Yeah. So, so this is the potential, right? So this should be 0. This is 0. So suppose this is the total energy of your system, E. Now, then that the kinetic energy is the highest at this point, right? Classically. And it's 0 at this point, right? So as you can see, this system the particle cannot escape, this region, right? In other words, the particle is a bounded, it's a bound, but it's a bounded system, right? So you'll see that when we do wave mechanics, that the wave function of the particle will be given by a function which has some form like this. Basically, it's non-zero in this region, and it goes to 0 outside. Okay, we'll see that those are the quantum mechanical version of boundedness has to do with the fact that the wave function necessarily has to be contained within a specified finite region of space. Okay.
Okay, sir. Actually, the question was I mentioned harmonic oscillator, but the question I was really asking about, I just checked. It was a free particle in a one-dimensional box of length A.
Right.
So
Okay. Yeah, that's a very good question.
thus it, like they said, impose the Sommerfield-Wilson
Yeah, I
quantization.
used free
Ignorant.
particle, but actually it was not free. It's a misnomer. I used because the potential was that it's infinite and it's 0 underneath. Inside, the particle does not feel any potential. So,
Yeah.
it goes infinity here and it goes infinity here, the potential energy. So although I called it free, what I meant is that inside, so suppose this is say 0, this is a by 2, this is minus a by 2, that the potential inside this region is 0. Outside, it's, when x is between a by 2 and, or let me just not use equality, minus a by 2, okay? But otherwise, it's infinite otherwise, okay? So even though it's quote unquote, it doesn't have a potential energy in between, it is still a bounded particle, okay?
Sir, if bounded by the length,
Bounded by the fact that there's infinite potential well. It's inside a well, right? I mean, if the particle wants to go here, then it must have infinite energy, right? And that's not physical.
oh, so that is the boundary.
Yeah, exactly. So this is the boundary. This is the boundary. Okay. So it's like, so this is the potential. Suppose this is the potential, but suppose that this height is infinite, right? So wherever the particle is, it can never climb out.
Okay. Okay.
Oh, good. Any more questions?